Hello physics. Today we're going to be talking about free body diagrams and also Newton's third law. So a free body diagram shows forces that are acting on only one object. So keep that in mind that when we do a force diagram, you can only take a look at one thing at a time. So sometimes you may want to make multiple force diagrams to understand what the question's asking, but each time you must only be looking at one object at a time. And we'll go through what that means. You can only look at the forces on the object, so it's on the object, not what the object is doing to something else. So we only look at one object and look at what's affecting it. So we're looking at kind of what is making our system do what it's doing. So we will be drawing a box, that's the object, and writing the forces that are acting on it. Some things that we're going to do later, probably next week, is we're going to draw marks to show forces are equal to each other. So if you see on a force diagram that there's two arrows going both ways, and they both only have one tick mark, that's indicating that they're both equal there. If this one had two tick marks and this one had one, then this one is going to be bigger than the other one. So that's kind of how those tick marks work. Now again, we'll look more into that next week. And they have to be going the opposite direction, but in the same component. So that's how those tick marks work. So you can't have one and one here. Those would not be equal. Those just mean that this one was the first one maybe here and the first one here. So they have to be going the opposite direction, but in the same plane. So I'll talk about sometimes that we have the X plane and then the Y plane. Y plane being like on a graph goes up and down, the X plane going side to side like on a graph. So keep those in mind that we're looking at the Y components, and then we'll look at the X components as well. So a couple things to note is the notation for free body diagrams. So with free body diagrams, we have the box. This should be the system and the object that the forces are acting on it. So you will want to write in what the system actually is. There are arrows. The length should indicate the magnitude or the strength, of the force that's acting on it. And it should also indicate the direction the force is pushing or pulling the object. So, one thing that we'll look at is gravity. So gravity pulls objects down. And so we would have a gravity force arrow that goes down like this. So that's how those arrows are going to work. We do have to have a certain way we write it, and we write it this way. It's F-type on a system by surrounding. So that sounds a little strange, but once you get used to it, it's not too bad. But if we think of an example like a book on the desk, we would say F gravity force on book by Earth. So if you notice that it's on the system, on the book that we're looking at, by the Earth. So the Earth is what's causing the gravity force. So that's why it's by Earth. This just tells us where the forces are and where they're coming from. It's a lot easier to keep those in mind and a lot easier to understand how the objects are interacting with each other. But let's take a look at a couple of things. We are not going to do the writing the force in quite yet. We will actually do that next week. But let's just have an idea of where forces would actually be at. So here we have our tractor pulling a log. And so we're going to say that on this one that our system is going to be the log right here. So this log here, we can only look at forces that are actually going to be touching the log or would have a field force with the log. So here's kind of the deal. One thing that we have to think about is what is actually touching the log? Well, we can see here that the ground is touching the log, so there'll be a force there because the ground and the log touch each other. And we can also see that this rope is touching the log. So one thing that we can kind of get rid of and not worry about is this tractor here. So that is something you'll have to get used to, is that we can only look at forces that are either touching the log or would have a field force with it. The only field forces that we take a look at is gravity. We're going to see that almost every time because gravity is happening all around us on the Earth. We also have electricity. We won't be looking at that very much. That's more of a physics 2 thing. and then also magnetism, which is also a physics 2 thing. So we're really going to focus on gravity as the only field force that we have. So we see this log here, and we can probably make a few assumptions. If we only look in the y component, we can tell that it's not moving here. And so when things are moving up and down, we say that that part is at rest. And when things are at rest or constantly moving, we know that they have something called a balance force, meaning that the force going this way in the y component and the force going this way in the y component should be equal to each other. So we don't maybe know what those forces are quite yet, but what we can do is just do the forces that we can kind of put a outline there of what we can see. So I'm going to make this just a little bit thicker here. So we know we have a force there, and we also have a force here. They should relatively be the same length. If they're not quite the same length, it'll be okay. It's hard to do that on this program, but try to make them similar because they're not, the log is not moving up and down. It's only moving side to side. Another thing that we could probably figure out is that this tractor here, this log here, it looks like the tractor and the rope are actually moving and the log are moving at a constant speed. It's not like it's like speeding up and then slowing down, speeding up and slowing down. It looks like it's relatively keeping a constant pace. So when things are moving in a constant velocity, they also indicate that we have balanced forces. So these going left and going right will also be equal to each other. So we know that we have a force going this way, and that force is from this rope. And then we know we have a force going this way, and we can maybe think about what that is, and kind of probably some deduction. You can see that this is a ground, and we know that when we are moving on a surface, we have something called friction. And so we know that friction is trying to get us to stop moving. So since we're moving this way, the friction force is going to be pulling or pushing us this way. In the up and down, the down is going to be gravity. So we know that gravity is always pulling us toward the center. So we know that we're going to be going straight down with gravity. So this log is also being pulled straight down by gravity. And this force here may be hard to note, but we can see that the ground and the log are touching each other. So there has to be a force there. So this here is a force from the ground to the log. So we're not quite sure what all those are yet, but we can get a nice picture of this. So this is one of the free body diagrams. Let's look at one more that's a little bit more difficult because it's on an incline. So the thing about this is that you can start to take a look at this. Is going to look at the car, and we have an incline here, and we can make probably a couple assumptions. We can probably figure out that this car might be moving this way, and so and it's not moving in the up and down. So we will still have again a force that goes up, but the thing about the force that goes up is that it has to be with this one here. It's going to go straight up here. Let's see if I can get that. And then we also have gravity pulling us down. So gravity is going to pull us down this way. Now we can see here that this is on an incline. So we know that there's some kind of force probably pulling us up this way or pushing us up this way. So we'll have the arrow kind of go at an angle here. And then we know that because we are, moving this way, and we know that there's probably going to be some kind of friction force that's forcing us to go the other way, we will have another force that goes this way. Woo, not that way, this way. Now, we don't know quite yet if it is equal or not. We could probably make the assumption as a stop that yes, it would probably be equal for us on both sides, or even if it's constantly moving. But if it's accelerating or decelerating, then we have something different. This week for your practice, you'll have a couple of these, and they're going to just be basic ones, and it's just taking a look at what is actually affecting everything and to see if there is a force on either side. So that will be what you'll be doing tomorrow. So you don't need to know what the force types are. I'm just kind of seeing what would affect an object. Then last but not least, we're going to take a look at Newton's third law. In middle school, you were taught that for every action, there is an equal and opposite reaction, which is not a bad way of saying it, but the problem with that is that it doesn't give us a complete definition, and since we are going through physics, we need to have a complete definition. So this is what we know now, is that for every interaction, there are two forces acting on the two interacting objects. The size of the force on the first object equals the size of the force on the second object. The direction of the first is opposite of the direction of the second. Forces always come in an action-reaction pair. So that was a lot there. So here's kind of what the deal is. If I am holding my phone up like this, my hand is putting a force on the phone. And so that is going up. Whereas my phone is putting a force on my hand, and that's going down. So we are taking a look at that on the phone, there is a force going up and down that's the same. We're actually taking a look at the force that my hand is putting on the phone that goes up is equal to the force that the phone puts on my hand. So it's a little bit different way of looking at it. And here's a couple examples that we can look at. Example one is kind of pushing on a wall. If I push on the wall, the force of me on the wall is going in this direction, but the force that is putting on me from the wall is going this way. So my force on the wall is going to be equal to the force that the wall puts on me. They're going in two different directions, but my force on the wall and the wall's force on me is going to be equal. Sometimes, and so that is how it's going to look. Sometimes we can see it in a different way, as in with kind of like kicking the ground with a skateboard. The force of the foot on the ground is going, down-ish in the diagonal, is equal to the force that the ground is pushing on me. And so we have those nice action-reaction pairs on it. I pushed on the ground, and so the ground pushed back on me. Both equal and both in different directions. And last but not least, the last example I have is if you're in a boxing ring and you are fighting, the force that the boxer's hand puts on the guy's jaw is going to be equal to the force that the jaw puts on the hand. Now, that probably doesn't seem right because we know there's going to be some movement, but there are other things at play that we also see that allows for the movement to occur. But anytime you have two objects interacting with each other, they both have forces on each other and they both will be equal. And that's a really cool thing to look at because it helps us a lot with math and it helps a lot with that interaction. So we will be looking at these laws more next week, but this is kind of the first round of looking at it. If you have any questions, please let me know and have a great day.